Okay. Or they are not coming because I told I will ask them. But they submitted. I can see so many of them submitted. Then why are they so much worried about it? Yeah, so I think I will keep giving you some of these quizzes. It is basically there is no marks. It's just to keep you. Uh, uh, okay. Yeah, so that's what I told you. Know that if plus z is of this form, and minus z is this form, then how do you work out the plus x and minus x from there? Yeah, can you tell me how will you work out? Someone else can also tell. Anybody. So I showed you in the class that if plus x plus z is like that, and minus z is like that, then you can work out plus x to be 1 by root 2, 1, 1, and minus x to be 1 by root 2, 1 minus 1. Did everybody follow that part? Then why I am just going the other way? So how did I go from here to here? Hmm. Hmm. Yeah, so I know that plus x from that experiment is 1 by root 2 plus z and 1 by root 2 minus z. So I know minus x is same with minus sign, right? So what if I plug this in? What should I get? That's all, right? This is a legal plus z and minus z. Because the only rule I have to satisfy is that they must be orthonormal, right? Once I satisfy that, it doesn't matter how I represent them. Okay, so it is just so this thing is called z basis because here the z looks like there is a reason for saying that because I'll show you when I write down the z operator, it becomes diagonal in that basis. That's why it's called z basis. Now if I would have chosen this, then the x is like of this form 1001. So this is called the x basis. So like that, so you can represent in anything in any basis. It's a matter of choice. Good, good that you asked. So everybody follow that much? Okay. So uh, yeah, so this is very important that you have a strong grip on linear algebra. I mean, you might say that why do I need to learn it outside the class, which means like in summer or somewhere else. Not so whatever is needed, I will do in the class. That is true, but the fluency is important. So it's like imagine this course would have been in French, okay, and then you are learning French and quantum mechanics in French at the same time. Then how difficult would have been that? So this is similar. So linear algebra is the language of quantum mechanics. If you are already fluent in that, it's very easy. If you are learning that at the same time as the course, then it is one step more difficult. Now that being said, there is a real story behind that. So when Calcutta University was first given, like had the first Indian chancellor, Indian vice chancellor, Ashutosh Mukherjee. So that was, I think, at the time of First World War, between First World War and Second World War. And he thought that this Calcutta University, there should be courses um, on these modern topics like quantum mechanics and relativity. And those days, all the important paper in math used to be published in French, and all the important paper in physics used to be published in German. So if you, and there was no textbook, the subject was not just developing. So if you have to teach those topics, then you have to first translate, first learn German and French, translate it, and then teach. Okay, so you can imagine how difficult it is because it's so confusing already. On top of that, you are learning it a language which you don't understand well. So then you will all the time you will think whether I misunderstood because of the language or actually I did it is something else. So this job was assigned to two guys. One was SN Bose, another was Meghna Saha. And they were just MSc pass, so they were like 22-year-old. Okay, and that's what they did. So they learned German and translated those papers from German to English and taught that course. Okay, so you can imagine what was the uphill task to them. Now there is no reason to make it that difficult for you. Okay, so learn linear algebra properly, such that you are not stuck by the barrier of language in this case. So it's simple. You already learned. Just spend some time with it. Yeah, somebody is saying something.
Yes, sir, the board is not very clear. Can you write it a little bigger because the board
Write bigger.
seems a little blurry.
Okay, this
Yes,
board is
because it
actually
is not
similar,
very
right?
visible.
So just writing big is enough, right? There is no other problem like yesterday.
No, sir, it's just because of the whitish thing. I mean, on top of the board. That's why it's not
Too much
very
white.
clear. Whatever you're writing.
Yeah. So can one of you do the following? Like, can you just watch this? Any of you watch this, and I will clean the board with this one. Then I think this problem will be a little better. Yeah, it will be better for me also because I have a lot of dust allergy. This chalk dust is problematic. Okay, so we will continue. Okay, let him come back. No, meanwhile, questions. So there are two approaches to do this part. One is a radio mechanic approach. So I call this the radio repairman approach. So in my hometown, there was a radio shop, radio repairing shop. And the radio guy, that guy could repair any radio. Very good, very efficient. But he didn't know what is a capacitor, what is an inductor. Okay? So he knew the functional relationship between them and can repair within the constraints, within that constraints any radio. So given our linear algebra background, I think I will take a bit of that approach. Okay, so where you know how to use stuff, what is the functional relationship, but to go one level deeper, you need this radio maker approach, which means this person will know that out of all the ingredients in the world, what to pick to make a radio. Okay? So I was initially thinking to do it like that, which means I try to build up the formalism, try to tell that why this thing looks like that, what are the choices you have, and why did you pick that particular choice. But I think it will be more efficient now at this current status to tell you what is what, and then hope eventually you will get the builder approach. And at this point, I think it is useful for you, those of you who want to be serious with physics, you try to think about it from the creator's point of view, like someone who is creating the formalism. That's why I suggest to read this Didak's book, even it is very difficult. That not very difficult, but more difficult compared to other books. That since Dirac developed this bracket formalism, you kind of get a flavor of what was he thinking. That why did he do that instead of something else? But that makes things a little weird and complicated. The flow is not very linear. So I have now, given the situation, I have decided to not follow that approach, but rather follow a repairman approach, which means given the things, given the constant, how to play the game, okay, rather than developing the game. Okay. Okay. So the first thing we said that vectors, so states, much better, are represented by vectors in a complex projective space, which we call as Hilbert space. Okay. And And we discussed that for every state, there is a dual state, which is useful for mathematical purpose. And so let's just call them Bra and Kate. Every representation of a state has a dual representation. It's a representation, not that it's another state. Now, the second thing we learned is the concept of basis states, which we know borrowed again from linear algebra. That tells you that every state can be expressed in terms of them. So physically, they are basically all the possible independent outcomes of an experiment, which was plus z and minus z in case of Stern-Gerlach. It could be anything, and they are basically we decided to represent them by what we call as basis state in linear algebra, and from there we learned a couple of other things that so these basis states or basis. So whenever I say state, always this is implied, a quote unquote state of quantum mechanics. So these basis states are basis vectors. Okay, so they are basically, we define them properly. They are basically linearly independent set of vectors in a given space, and how many of them are there? So number of them gives the dimension of that Hilbert space. Okay. So this is what we learned. I think everybody is totally in sync with this part. Then we learned the role of an operator. So a measurement is best expressed by an operator. So what do I want from a measurement? We want three things. We want the measurement to send one state gate to another state gate. Okay? That was the first thing. So operator does that job. Second thing, we want to somehow know that that it can give me a number also. So we will see that this job, for that job, we have to go towards something called eigenbasis. So let me just go talk about it once more. So I wanted the act of operation, I want this to give me another state. Okay, everybody is in same page with that statement, right? Now I want one more thing, that this act of operation will also return me a number that I measure in my device. So it turns out there are some states. There are some state which doesn't do anything but give you a number. So those states are called eigenstates. And you also want them to include the situation that if my input beam is plus z, then if I measure z, I will always get plus z. So that means plus z remains at plus z. So that fact needs to be represented somehow. So this is a candidate for that. Okay. Now there is one more thing we want from a operator measurement business, is that I want to represent, I want to describe an operation or act of measurement with a in a statistical sense. That by that I mean that if I measure z many times in such a state, in an ensemble of such a state, by ensemble I means identically prepared similar states which you measure separately, but it is not like that. It is not like this, that you have the same electron, like the same electron, and you measure again and again on top of that another SZ, another SZ. It's not like that, and it is neither like that you have a bunch of electrons which you are measuring, and it's like that, not like that. So theoretically speaking, what I'm talking about, it's one electron at a time, but many such identical electrons, many identical copies. So if you can do such an experiment, then you want an average, a quantity that is the average of such measurement. Okay, such I need to write down, identical copies. Now this is you might ask that how do I guarantee that if I have 10 electrons, they are identical? So this is the problem of coherence. So one of you was asking this coherence point. I can't see that person. Anyways, so is you are you here? That who was asking about coherence? Yeah, I don't remember. So then the question comes that how do I know these 10? I prepared 10 electrons and I sent one at a time and did the experiment. How do I know that they are identical? So it's not so easy to know actually in reality. So there are complexities over that, but for the but it's possible to do that. And let's assume we know that, so they are coherent. So I represent these as some expectation value. And we also argued that the expectation value must be the value you get from these measurements times the probability, okay? Which is usually, which is in this case, is the probability amplitude square for and that to be in this state, and that can be represented as some DAV. Okay? So, yes. No, no, it doesn't guarantee. Good question. So I want to make that point that if I measure, I get a number. Okay? So what I'm trying to say that how you can get a number out of a vector and a operator is by if that vector is the special vector, which is an eigenvector. Okay? So one is a state is a vector and 3 is a, yeah, so 1 and 3 are totally two different points. One is just saying that a state is a vector and 3 is saying that when you do a operation, then you go from one state to another state. So for example, in this experiment, you go from psi to plus z, right? You go from one state to another state, right? So I want a mathematical description that what happened here that took a state and gave me another state, right? So the mathematical object that does that is an operator. So this much is clear, right? So this statement is clear. Yeah, I'm coming to that, but this much is clear, right? Okay. Now I'm coming to the next statement. Okay. So next statement, let me say it a little differently. Let me say that I do SGZ. I'll get full surety that I'll get plus Z. Right? You agree to that, right? So there must be a special each operator. So whatever this is the same operator as that, right? So there must be some states for a operator which returns the same state. Okay? So they are eigenstates. So up to this much I wanted to make the case. Now I will come to further point that what guarantees me that why I need even eigenstates to begin with is not just this, it's more than that. So that's what I will come. But up to this much is clear, right? Yeah, very good. So you should keep asking such questions, then only some clarity will come. Last point means, so this point, right? Can you explain it? Yeah.
Once we know that, then it guarantees that when we measure it again, there will be some identity.
So each operator must have some state that after a measurement it stays in that state, because normally a operator takes you from one state to another state, but some states doesn't go to another state, it remains in that state. So those states you know that such things exist in linear algebra, they are eigenstates. Make sense? So in the space of all states there are some states. So this is the space of all states in that Hilbert space, okay? And there are many states. Now there is a so now I have taken an operator. I have not yet written what operator this at, so let me just write it as a generic abstract operator. Okay? I have not written yet the form of that operator. So if I take a state pass it through that operator, I should get another state in the same space, right? I should get from this point to another point. But there are some states for which if I take it to A, I return to the same place, right? Those states are, we know them to be eigenstates of that operator. Make sense, everyone? Okay, so I am again going to the builder approach, but this is still like these are the kind of things people looked at and developed a formalism. It's like most of the time in most textbooks you will find they will just give it to you. This is that, and just play the game. But if you look at Dirac's book, he argues it like that. He said, "Why did I choose this? Why did I choose that?" Like that. That's very interesting, and it's useful to learn that because maybe you will do research and develop a theory for something else, right? So it's good to learn that what was going on in the head of the person who was making it. Okay. Okay, so now so we learned that a operator must do these three kind of things. Like there are three kind of things I want from an operator. First, I want this thing. One state goes to another state. Some states doesn't go anywhere, remains there, and there must be a quantity which does this job, which represents that if I do many measurements, then I can calculate the average, and that average I should be able to represent it like that. Okay, so this is what I already talked before. So now let's go a little further and learn that what kind of properties you need from linear algebra. Only that much. Okay, so yeah.
State itself is a vector. And you also know that out of the whole space, some of the states are the eigenstates that we are looking for.
Yeah.
It means that there are some states where you will not get any kind of measurement.
No, why? What?
Like they are not eigenstates. So how can we measure?
So they are yeah, good question. So some states are no, it's not that you won't get a measurement. You will get a measurement, but it is not that state itself. So let me, since you asked, let me go over that. Instead of going systematically, let me just give that answer. So you want to have one more point, is the idea of basis states. So you know this, that eigenstates of any operator forms a basis. Right? This statement everybody knows that. Okay, very good. So let me take let's just speak about it completely mathematically. Then I'll come to make the connection with the physics. So let's say I take an operator A, which has a eigenspace. So A acting on A gives you this. Okay? So these A operators constitutes the eigenbasis. There are I of them. Okay. So that means any state in this space can be expressed as CIAI. Okay. Everybody in the same page? Okay. So now that means if I act A on psi, I get CI AI AI, right? Because the A act on AI will use this, will give me that. So that means I can say that, so this implies that, so this fact is represented in the context of quantum mechanics by saying that if I take any state, which is a superposition of other states, of basis states of an operator, if I perform a measurement, it will collapse into that state, okay? Or it will jump into that state, AI, of that particular eigenstate with probability amplitude Ci. So then if I calculate psi A psi, I will get I and J AJ CJ AJ. So I will get AJ CJ star. So this should be also a star, but I will tell you a little later that I will choose this A to be a Hermitian operator for which this A is always a real number, because a measurement must always give real number. So then that is CI AI AI. Now all these are scalar. I take out AI AJ are orthogonal. Why they are orthonormal? Because of again for the fact that A is Hermitian. So A is Hermitian. That means two things will happen. That means AIs are real and AI AJ is delta ij. It doesn't guarantee delta, it guarantees that they are orthogonal, but I am making them orthonormal also. So that means that is Cj square Aj sum j. Okay? So this gives me exactly what I want. Okay? Now, if you didn't understand yet, let me give an example. So I said that psi is C1 plus Z plus C2 minus Z. Now, if I act a Z on it, so it should give me plus Z with probability amplitude C1 and probability, so probability amplitude C1 and probability C1 square with an eigenvalue with or with a number which is this some number. Okay, let me call it some. In reality, I'll put it h bar by 2. Is it? So these two facts are basically in sync with what we are seeing from the property of linear algebra. So if you want to use these properties of vector, matrix, and operator for our context in our language, that is the connection. That an act of measurement basically throws the state into or projects the state into one of these eigenbases of that operator. And once it throws there, then the second measurement will not do anything else. Imagine the many world interpretation. Once you are in one world, you cannot go back. Which means if you perform a second measurement, so let's say you did that, you did sz psi, you landed on plus z, right? Then you do another sz, you will still get plus z. You cannot get out of there. Okay? What happens if you do a x? That I'll come later. That comes, then it comes the relation between two different operators. And a lot of things depends on how are you doing it. So everything is clear so far what I said using the properties of linear algebra and quantum mechanics. Yeah. Yeah, no, in the sense that we want, see, it's again a construction that we want our operators to return one number. The operator must return a single number. So we choose that it should be Hermitian, which returns a real number. You could have chosen to formulate the quantum mechanics using anti-Hermitian operator also. Then it will be a pure imaginary, a single number but pure imaginary. But when you do that, some other problem happens that you will see when you will do dynamics. Hermitian is particularly useful. It will give you some better formalism. So I want a single number, not a complex means two numbers. It should not be like that. So that is why I am constructing it like that. But that being said, there is a catch. There is a whole branch of physics called non-Hermitian quantum mechanics. You can show that there are some non-Hermitian matrices which can also give you real number. And then you must ask that who told that nature is not going to follow our rule, right? Nature will follow any rule of whatever gives the real number. If you are measuring a real number, in principle, you should also be able to allow non-Hermitian. And that's a whole branch of physics. So non-Hermitian quantum mechanics. But let's not go to that. It's a bit tricky. Let's play with the standard textbook route. Then we'll go back to that sometimes later. Everybody is in the same page with this idea that why this structure of linear algebra is particularly suited for this description of this kind of an experiment. So you can go even more. So I'm again taking a little unusual approach, but if this point is totally clear to you, I mean, I save many lectures. Okay, so make sure you This is the whole idea, and this is the whole course is basically repetition of this idea. So it's very important that you get that fully. So that means what I'm trying to say, that I have a device which measures the operator A. Okay? Now, which measures something that I represent by the operator A. So that being said, it reminds me something also something funny. So we had a teacher in school who was very strict in grading, and even if you think you wrote everything correct, then you get very bad marks. So he once told me that I wrote ideal gas follows PV equal to nRT. He said, no, ideal gas does whatever it does. You should write the equation that describes ideal gas is PV equal to nRT. So, and he cut marks for that, for writing. So this is a description that fits with the experiment, okay, to be more honest, rather than saying in any other language. So that means, so let's say there are n channels. This is a Stern-Gerlach with n channels. So what can it give? It can give A1, A2, A3. Yes? Oh, attendance, okay. AN. So if you take a particular psi, which is sum over Ti AI, so it means this state psi is a superposition, which means this state psi is in all these states AIs at the same time with probability amplitude Ci. Until measured, it's like that. Right? Now, when you perform a measurement, and let's say you have another channel too, or no channel, just some screen. So then in a given measurement, whether you get A1 or A2, that means it collapsed into that particular state. Okay? And once you measure that, then if you measure A again on top of that, you take this output and measure A again, then you keep getting the same thing. That is the picture. So that is what I just described in this language. So that equivalent statement is, if I perform A measurement, it collapses to one of the eigenstates. Let's say it collapses to A2. So if it collapses to A2, so your device you should measure the number A2, and with probability amplitude of many experiments, a probability amplitude is C2 mod square. The probability is C2 mod square, probability amplitude is C2. Okay, everybody is in sync with this description. So I will precisely show that how you can fully construct this matrix in a very, as you know the matrices like 2 by 2, 4 by 4 form, and how do you exactly perform the calculation show. Okay, so if you have understood and internalized this point, then it is my job is very easy. Rest is basically just manipulation. Okay. So anybody who is uncomfortable with this can raise hand and we can discuss it further. Yeah. Yeah, I'm just generalizing. Yeah. Yes. Yeah. Hmm.
That doesn't mean that measurement actually will collapse to other things. The presence of one state doesn't alter the state of other.
No, because these worlds are not communicating. Okay. What if they do? Then you get a Marvel universe, DC universe colliding, right? So if they communicate, then this point is then it is not consistent with the observation, right? To be serious, like because the fact that so if I go through this Everett's many world theory, right? Because what we know, that once you know that a cat is dead or alive, there is no way to go backwards or know what happened in another world, right? So that is what is needed to make sense of these observations. Once you get a plus z, it is plus z. So this is, again, let me repeat it again. It's again, you can give any analogy. You can think in terms of plus z minus z. You can think in terms of double slit, whatever you like. So the electron is passing through these two holes. or the electron is in two defined states, plus z and minus z. We need the description to be like that, that they are both at the same time until measured. But when measured, then you won't see the strange thing, right? So this is a very, but what you see is dictated by this fact. So if I repeat this in terms of the double slit, it tells you that when, if I observe, I'll always observe a whole electron, a whole particle, not a wave or anything else. But to make sense of that, what is the probability that particle reaches at various points of the screen? To explain that, we need to think that this is a wave and it is passing through to both holes at the same time and interfering with itself. Okay? So this is the description we are trying to formulate. So the part that we cannot see, that is the probability amplitude. But that controls what you can see. Okay? And with various experiments, we also tried to convince you that there is no way, whatever you try, you cannot see which hole it passed through. If you can see somehow, then then up to that point, to calculate that what is the probability of this comes here. So up to that point, you have to use the amplitude language. But then once you observe, then it is again like a classical object. Right? This is the most strange part of quantum mechanics, and it's very important that you get this point without any ambiguity. Okay, more questions? It is strange. I cannot say that I can explain this to you because nobody knows how this happens. Nobody can explain. But what I can tell you that what is known and what is the picture. So that much is my job. Okay. Okay, questions, more questions. Once you get that, quantum mechanics is not that hard. It boils down to, because the formalism is so nice. So there is a very famous statement by Anderson. Anderson is one of the pioneer of condensed matter physics, or not one of the, he is the pioneer of condensed matter physics. So he said, the job of a theorist is not to solve a problem. I mean, it's of course to solve a problem, but he meant to say not only to solve a problem, but to set up the problem in a way that any fool can solve it. So when you set up this problem, set up the formalism, it boils down to diagonalizing a matrix and solving a differential equation. This is the most powerful part of this whole thing. Then you put it in a computer and calculate complicated stuff and all that. So this part we need to understand, that how you connect this and set up the problem, that becomes a easy solution. Okay, good. So I deviated from my lecture note, but I think it was useful because I straight came to the point. Okay, so there are two more things which I wanted to say according to the second line of my. So now I'm moving from the first line to second line of my note, and in between all these things randomly happen. So, but it's good that you then I save a lot of words. So let's talk about the second line. So don't get overwhelmed by the notation and algebra and all. These are easy. You need to spend time, of course. It is like learning a language. Learning a language is not hard. Anybody can learn. Right? But the hard part is to know this, make this connection. So I have seen earlier people are saying, "Oh, too much algebra, too much calculation," but that is not the hard part. It feels hard when you don't give it enough time. So if you give it time, of course, it becomes easy. Like you cannot learn a language by sitting once a week, right? You have to all the time watch movies, talk in that language, then only you learn the language. So it's like that. So spend time with it. You will, of course, the formalism will become very easy. But this part is the tricky part. This is not a state function of how much time you spend. It's a little more than that. Okay, so the point I wanted to make is that, so we describe this quantity, EAP. So this is, we call it expectation value. So what is this quantity? This quantity we also described it. It is the um, it is the average value to get after measuring on an ensemble. By ensemble I mean identically prepared system, and this is called expectation value because of course if you perform the measurement then you think of probabilities, but that's why it's the value you are expecting, right? That's what, because that's why you are allowed to use till the probability amplitudes. Okay? So there is an interesting property of this quantity. So V, now let's think mathematically, and we'll see in a moment that how it comes automatically also in the physical context. So if I take a sum of two operators, the value of the sum of two operator is equal to sum of the value. Okay, this is true for any, easy to see that it is true for any such operators. Straightforward, and you also expect that intuitively in classical systems, that if you add two if you add two values or two observables, then what you get is sum of their what you could have gotten them individually. Okay? But this is not true. Even in mathematical sense and physical sense also there is a meaning for that. This thing is not, first of all, this thing is not mathematically same as this thing. Neither this thing is same as VAV, VBV. None of these are same. So that means the product of values is, the value of the product is not same as product of values. And it also matters what you measure first, whether you go A and B or A. So this is the general property of any operators. Now this I am saying mathematically, and physically you also know it to be true, that if you take a state and you perform a X first and Z later, or a Z first or X later, is not necessarily same, and also you cannot just take a product like that. Okay, so this is what I will now further elaborate, that what does it mean and how to represent this fact in which is special in quantum mechanics. Okay? So everybody with me up to this? Okay, now two more points which I think I mentioned it in a passing remark, but I think you need to also know this, that these operators, these A, have to be Hermitian. So this I mentioned last time and this time also. Why? Because a Hermitian matrix has two properties. One is AV, so let me call it VVI. So VI eigenvalue is real, another is VI Vj is delta Ij. So we'll use this property, but we want this to happen because I want to make sure that if I take a psi and express it in terms of some, earlier I used the notation A, but let's use V since I'm using V here. If it is V, then I can easily represent that what is the probability amplitude of getting, let's say, V10 in this sum. Right? What is the probability of getting V10 if I measure the operator A on psi? Can somebody tell me what is that? What is that from this expression? Right. Mod of C10 square, but I represent it as V10 psi. Right? So the probability is that square. So that is mod of C10 square. Right? So that will only happen if these VIs are orthogonal. Right? If they are not orthogonal, you cannot write it such a way. So that's why also it is very desirable to have this basis of coming from somewhere which is orthogonal. That's why I want this to be this operator to be Hermitian also. Okay. So this is what I wanted to convey. So now let's go on and talk about what happens when there are two operators involved. Then it comes to this question that whether I measure one of them first, another of them second, then how that changes everything. So before I do that, let me talk about again properties of all the properties we know from linear algebra about two operators when two operators are involved. So first definition is something called commutation, which you probably know already. Okay, online audience, are you following everything and is everything clearly visible? Comments? Can you hear me? Hello? Oh, not visible. Why? Okay. Was it the case throughout the lecture? Can you speak up because I am not always looking at the screen. Can you? Okay, when I write smaller, it's not visible clearly. Okay, can you speak? I mean, it's much better if I have a conversation.
Yes, sir. Actually, we can't see the board properly when you write smaller.
You
Like
can't see the bottom of the board?
no, we can see the board, but when you write it smaller, we can't see
If I
properly.
write small, you can't see properly.
Yeah, the Hermitian properties and other stuff.
Is this a
Like
problem of today's lecture or it is a problem always?
today's lectures only.
I think there is some connection problem then again.
And
Okay, for this reason, I think it is still probably have one day class there because these people will totally miss out otherwise. But anyway, let's see what can we do. I will let them know formally because it's very difficult to always remember this. I'll try to write bigger because we have only one board also. How many times will you wipe? So, so first thing is commutation. So commutation means AB is equal to BA. Okay. So this is just a name of this property. If that happens, it's called commutation. We'll see why it is important. Okay. Second thing is another object called commutator. So AB minus BA, that we usually it is referred as, sorry, this is just AB minus BA, usually it is referred as AB. This is a operator called commutator, which you just take AB minus BA. And this is of course meaningful only when if AB is equal to BA, then it is just 0. But if this is not equal, then it is non-zero. Then it's a meaningful object. Okay. So now if a non-trivial statement. If two operators commute, they have a common eigenbasis, or they have common eigenstates. Which means, what do I mean to say that? So if A is like some Vi, then B will be same Vi, but this can be defined Wi Vi. This is true if AB is equal to 0. This is a theorem, and I will give a less rigorous proof of that. Well, somewhat rigorous proof of that, but everybody understood the statement. Anybody already know about this? You knew about this? Oh, okay. Oh, very good. So okay, so we will see that there is a very important consequence of this statement, and it is so cool. Yeah, somebody else was saying something. Huh? What? Yeah. This will link with uncertainty. Very good, and then it will give you a very useful tool also, because then you will see that you can uniquely label the state. You can give a label of the state in terms of these two eigenvalues, V and W. And this is actually what is used everywhere. Like in chemistry, you might have learned this SPDF orbitals, right? They are nothing but eigenvalues of mutually commuting operators. They are, instead of number, they are given a letter, SPDNA. Okay? So it's very important, this idea. Okay, so so I will give you an exercise. to get used to this idea. So you know also about this kind of elementary linear algebra things that we write it here because it's not part of that. No, not that's what I'm saying. The eigenvalues need not be so degenerate means one thing. Degenerate means yes, eigenvalues are same of the same operator. So here you are probably trying to say that V and W are equal, right? So that not necessarily. So that is the statement. So V and W could be totally, they are two totally different operators. The only thing they share is eigenstates. Eigenvalue can be defined. They are totally unrelated things. So we'll see that when you do SPDF, one of them is orbital angular momentum, another of them is L square, this operator called L square, which is total angular momentum, another is LZ, L square LZ. So like that. So I will come to that. So actually, yeah, so that's why. So I'll give you examples. So do these two exercises. So the first is, so first is not related to this property, first is a general property. So take this matrix. Actually, I'll give you this exercise also in as a Google assignment. So check that if this matrix is Hermitian, first of all. So we will learn by examples. We will not go too much into theorems.
Sir, can you write it bigger?
I have to write bigger?
Yeah.
Yeah, good. Keep reminding me. Don't hesitate to bug many times. Every time I write small, every time you can feel free to do that. So check first this, saying find the eigenspectrum. So by the way, I was thinking these exercises are extremely easy to do in Mathematica. You don't have to all the time write 3 by 3 matrix, diagonalize it full by hand. You can do it in Python also, but Mathematica is particularly easy. So I was thinking of giving you a half an hour tutorial on Mathematica, but it cannot happen in the class time. So you can tell me what time is better. For example, maybe in next Monday I can start at 8, and since you have always something after, right, before probably but that's also good, then you have to wake up early, and that means you have to have a strong enough urge to learn. Okay, so that automatically squeezes the size of the class. And then I also know that I am working hard for somebody who is serious, right? I am willing to do all you want, but you have to also show me that you are serious. So I will give you an half an hour tutorial of how to use Mathematica. Then all these small exercises I'm giving you, they will literally become a 1 minute exercise. This one, I hope you didn't take more than 10 minutes to this set of exercise. If you took more than 10 minutes, then spend more time on it to make sure you can do that kind of thing very quickly. So second task is find the eigenspectrum. And third, eigenspectrum is value and vector, both. So third one is see that can you find a linear combination of eigenvector that is also an eigenvector. So this is to show that this basis, this is a basis. So if you can find such a thing, then that is you have some more elements in that basis. So is it true? So this is third. And fourth, find a transformation that do this U dagger makes it diagonal. Okay. So you know how to construct this U, right? If I give you all the eigenvalues or eigenvectors of a matrix, you know how to construct this U matrix, which will do this job. More, somebody from back. Yeah, how about somebody from back? Do you know how to construct? Do you know that such a matrix exists? What? Why there are so much blank faces? D is the diagonal, all a matrix whose diagonal entries are the eigenvalues. Oh, very good. Are you what? Why so much blank faces? So this is one thing I am telling you again and again. That it doesn't matter if someone is working like very hard but not regularly. So it's important that in any course, not just this course, because these courses are interlinked. What you learn there, it comes here and so on. There. So make sure you are not thinking that I will study one day a week and learn a huge. I'm telling you from experience. I'm not telling you as a teacher of quantum mechanics course. I'm telling you as a senior who have lived the same life before. From my experience, it always happens. So there were some courses in my masters which I didn't study, and there were some courses which I studied. Of course, but everybody has that favorite courses and not so favorite courses. And I have seen suddenly after, I did my masters at IIT Delhi, and we had 3 exams there, not 2 like you. 3 means minor 1, minor 2, and major. So that means we have to study at least thrice a semester. Okay, so even if I don't like the course, I have to study thrice, 3 weeks. Okay, and suddenly after the mid sem, after the exams, I started liking every course. So why do you think that happened? Because I studied and then I suddenly started following, which I was not following before that. So it's even if you don't like this course is not like a course which is optional if you want to be a physicist. So even if you are not like thinking that okay I will not use this that much, enforce the discipline of studying it regularly, then only you will follow. So probably something is taught in math method. Some people knows it, some people doesn't know it. It simply implies some people have thought I'll study 1 week before exam, and that will be a disaster. Okay. So the way to construct, the recipe to construct this U matrix is take the eigenvectors. So diagonalize the M. Do this exercise by hand. Then I'll show you my math. At least you should do once by hand. So diagonalize that M. Let me call it Mi. Okay. So this U matrix is basically these Mi vectors, these vectors written in a column. Okay. Then if you apply M on this, then each of them will give you that number times M. So then if you apply M from other side, then you get this diagonal entries. Right? Everybody follows this? So do this exercise by hand. You need to know the meaning of each operational. It is again, there is another end of this radio mechanics spectrum. Somebody has a full BTech but doesn't know how to repair a radio. So you should not be that guy either. Okay? So you should know operationally how to deal with this. So take this matrix, do this exercise. Then a second exercise is to do these statements you are saying. All these statements should come very naturally to you, not as an abstract statement, but as a effective proper statement. So second exercise, take 2 matrices. Okay, 0, 1, 0, 1, 0, 0. They are very simple matrices with lot of 0 and 1s. So B is 1/3. So if the online audience you can't see these matrices, I'll give my notes and also I'll post this. So you can also construct your own matrices. It's not that I have to take only my examples. So then check these things. So first is check if they commute. Second is find their eigenspectrum, both. And third is construct the diagonal form for A, some D, and show that the same matrix U, same U does the same job for D. So it is DA, this is DB. So then you know they have simultaneous eigenvector, but DA and DB are not equal. So that means their eigenvalues are not same. So check that. Okay? So do this, all these things. then you will have a understanding of what these things are. And I will just finish with one statement to connect all this mathematical exercise with a physical example. Is that so if you find, so I will connect this uncertainty thing also in the next lecture, but let's just finish this start. So there is this thing called CSCO. It's called complete set of commuting observable. What is this? So if I find a set of Hamiltonian, a set of operators, okay, which all commute with each other, with each other, and this is the maximum set, which means there is no further you can find in a particular Hilbert space. So then such a set is called complete set of commuting observables in that space. Okay? And if this set is, if such a number of such, so if n is equal to dimension of that Hilbert space, of C space, then this thing is, then these eigenvalues can be used to label a state uniquely. Okay? So this means also there is an unique, there is an unique U which diagonalizes all of them. Okay? There is one U, one set of eigen, they all share one set of eigenvector, and that can be labeled by their eigenvalues. So they can be labeled by their eigenvalues. They means those states, those eigenstates. Okay. And yeah, so you will see an example that H, L square and Lz. You have seen that in some context somewhere before, right? In chemistry or somewhere. So H is a Hamiltonian of a hydrogen atom or something. So their label is n, eigenvalue. L square has label L, and this is m. So these three numbers uniquely specifies the states of a electron in this kind of a hydrogen atom kind of problem. And you also need a third number, a fourth number called spin, okay, which is ad hoc, which doesn't come from this theory. You have to put it by hand. It comes from the theory if you include relativistic quantum mechanics. So here it is only NLM, and you know that this n equal to 0, so L can be this 0. If n equal to 2, L can be 0 and 1. And for each of these, it can be -1, 0, +1, all this. And this gives you all this SPDF business. Okay, we will learn this explicitly in this course after midsem. But I'm just giving you a motivation that this thing is forms a CSCO. And that's why you can use them to label all the eigenstates. Okay? This is the physical motivation of learning this, this kind of. Okay, that's all I wanted to do today. And if you have, I mean, class is over. If you want, you can ask questions. Okay, tomorrow I'll further elaborate on these points. It's like more what I wanted to do over these 2 days. I kind of covered it today conceptually, but today I'll further elaborate these, give more examples and all that, and that is what we'll do for this week.
So you said that any vector in the Hilbert space can be written as the basis of this eigensets, right? So how can we always say that this eigensets forms the basis for the Hilbert space?
Oh, that is a theorem. That is, if you have a eigenstates of any operator, they forms a basis in that space. Yeah, so that is, we can say that because this statement can be precisely proved, and I didn't discuss this.
If the eigenvalues are distinct, right? Then only we can say
So that there is a catch. There is a catch on that. So the point is, even if they are not distinct, even if they are degenerate, you can do something to make to find the Hilbert space. So what will happen? There will be in the distinct. If you know about this already, in the degenerate subspace, there will be infinitely many states which are good choice as a basis vector. So you have to choose two of them and normalize it using some orthonormalizing using Gram-Smith or something like that. Then it becomes a unique leveled choice, and we'll do that right next to next class. We will talk about the scenario when there is degeneracy, and degeneracy will create a problem like these two. So I can say that this U dagger will give me DA, but if there is a degeneracy, then this statement is not always true. So then we have to find that particular choice of states from that degenerate subspace such that this is true. I mean, this is true because we are not using the right choice. But there is always a unique set that exists, but that may not be obvious to find. That is the statement. Yeah.
So in actual physical, the eigenvalues.
Yeah, that is how you construct your operators. So because so for example, you will see that sz in z basis is written as h bar by 2. You put this by hand as 1 0 minus 1 0. No, this part, of course, how will you derive h bar? It's given by nature. How much magnitude of h bar? Actually, very in Hamiltonian and all this cannot be derived. They are always like it's an art that how do you construct a Hamiltonian that from a problem. Huh? Lot of things are there. Intuition, yeah, because you cannot this you cannot find, right? Your measurement will tell you there are two possibilities. What? Okay. So from symmetry, you can say something. Sometimes symmetry guides you that how many such possibilities are there. But how do you know there is something? So it doesn't come. There is no underlying deeper theory that tells you why there is a h bar of this value, right? So that is always a experimental input.
So we're only measuring the eigenvalue, not the eigen.
No, we are yes.
Eigenvectors are
Yes, we are saying that it is going to a state that is a
but
eigenvector.
that's an abstract quantity.
Yes, and it's not so abstract. You will see. I will put it in numbers, and there is also that's a good question. For example, in a measurement, let's say you are looking at a spin system. So what you actually measure is this quantity, right? Right. This is what you actually measure. Then what goes in here is what is consistent with what you measure. So let's say sometimes people do this NMR spectroscopy of a spin system in a lattice. So they will find some texture. So that texture is not a not something. Now whatever you can put. So whole quantum mechanics is a projective theory, which means there are many choices for a given observation, and how you choose them. That is, there are some guidelines on that. That why you choose this or not that. Right? It's actually many theories are projective. We are not just used to say that, right? Like even if you measure a position, it's depends on many how you define coordinate, where you put your origin, what is your initial angle, all those things. So, but this is a little more than that. There you see it. Here you don't know what you see. That's what I mentioned. A state is a prescription. A state is not the state of being. So there is no equivalent correct word for it. We just use the word state. Yeah. Yeah.
Then the first question we did, but the second question, two things that we were getting. Through the transformation, like TA equal to B when we were doing it. In the other case, when we were doing it by hand to find out that matrix, the one minus sign is coming out as extra. Like I will show you
What do you mean by extra?
Like let's say x1 bar and x2 bar has been given to us. So from here we need to change the basis here. So we need to come from 10012 to this thing.
Yes.
So first we found out the value of C1 and C2. Through that we got this new matrix that can define that. Now the transformation matrix that we can find by that this thing, like we can write x1 bar in terms of x1 and x2. Like 1 by root 2 1 0 and
yeah, it should be something of this form, 1 by root 2 1 by root 2.
Yeah, it came out like this. So similarly, we got like x1 bar.
So when
x2
you are doing complex number manipulation,
Yeah.
make sure you are careful about conjugates.
Yeah, so we actually got answer as conjugate of like
Okay.
like when we did it here by hand, like normal method
Hmm.
to find out the change in viscosity. There we got this answer, but minus was up and plus was here.
So what is the problem? I don't get it. Oh, you are getting different matrix in different ways.
Yeah, just a minus difference, like a conjugate of the.
That I have to check. I didn't solve the problem.
Because he also got the same.
Okay. Okay, I have to check. I didn't solve the problems. I just made them up. Okay. It was just to make sure that since nobody is talking, so I didn't know what's the situation, and I cannot proceed without knowing it. I have to check. If you can, if you know how to solve it, that is good enough for me. Like I'm not going to check whether you actually solve it or not.